Welcome to episode 14 in the Accident Theory series. Previously, we learned that tree-based accident analysis methods extend traditional domino models by moving beyond a single linear chain of events. These methods account for multiple interacting causes that develop over time, offering a more accurate representation of how incidents occur within complex systems. By accommodating parallel and converging causal pathways, tree-based approaches reduce oversimplification and support more thorough identification of contributing factors. In today's episode, we are going to expand on what we have learned and go into greater detail learning about fault trees. We will learn about fault tree logic, as well as how logic gates and truth tables work. We will end the episode with a case study to practice our skills. Hazard identification tools are systematic methods used to recognize potential risks, dangers, or threats in a specific environment, process, or system. They help organizations and individuals proactively identify conditions or situations that could lead to accidents, injuries, damage, or other adverse outcomes. These tools are critical for preventing harm by enabling a thorough analysis of both routine and non-routine activities, equipment, materials, and environmental factors that may pose risks. Hazard identification tools are widely used across industries such as healthcare, construction, manufacturing, and transportation to ensure safety, compliance with regulations, and the protection of people, assets, and the environment. One very important hazard identification tool is referred to as a fault tree. Fault tree analysis is a widely recognized and highly effective hazard identification tool used to systematically analyze the factors contributing to a specific undesired event, referred to as the top event. This method involves deductively identifying causal factors, organizing them in a logical sequence, and representing them visually in a tree-like diagram. The fault tree diagram illustrates the relationships between causal factors and their logical connections to the top event, providing a clear and structured framework for understanding the sequence of failures or conditions that could lead to the undesired outcome. Fault trees are particularly useful for analyzing complex systems with numerous components, especially when the system involves many small probabilities of failure. By representing these probabilities in a structured way, fault tree analysis helps practitioners assess the likelihood of the top event occurring and identify critical areas for intervention. Additionally, fault trees are valuable tools for mapping out the relationships between causes, prevention measures, and potential adverse outcomes, offering insights into both system vulnerabilities and opportunities for improving safety and reliability. In a fault tree analysis, the top event is placed at the top of the tree, serving as the focal point of the analysis. The top event represents the adverse outcome that the analysis seeks to explain or prevent. If multiple types of adverse outcomes are of concern, each outcome is assigned its own fault tree, allowing for a targeted examination of its unique causal factors. This approach ensures that each potential failure scenario is thoroughly analyzed and addressed. Practitioners in fields such as system safety, safety engineering, and risk management frequently use fault tree analysis to enhance their understanding of complex systems and develop effective strategies for hazard prevention and mitigation. The visual and logical structure of a fault tree makes it an intuitive and powerful tool for communicating risk factors and solutions to stakeholders, ensuring a collaborative approach to safety and system reliability. A fault tree is built using a combination of events, conditions, and logical operators known as logic gates, which are terms derived from Boolean logic. These gates define the relationships between different causes and conditions that lead to a specific outcome, referred to as the top event. Simply put, the top event is at the top of the tree, and all of the causes are at the bottom of the tree. How these causes affect the top event depends on their interactions and reliabilities. There are 6 different types of logic gates used in Boolean algebra, with the first 3 defining basic logical operators and the latter 3 being variations of the first 3. Let's take a look at the first three logical operators. And gates represent scenarios where all specified inputs must occur simultaneously or coexist for the resulting effect to take place. This means that multiple contributing factors are collectively necessary to produce the undesired outcome. For instance, a system failure might only occur if two or more components fail together, making the failure dependent on the simultaneous occurrence of all these conditions. Or in practical terms, in order for a fire to start, heat, oxygen, and fuel are all required in order for the reaction to take place. Or gates, on the other hand, describe situations where any one of the specified inputs is sufficient to cause the resulting effect. In this case, the occurrence of just one condition or event can trigger the top event, regardless of whether other inputs are also present. For example, a power outage might result from either a transformer failure or transmission line issue. Any of these conditions alone can lead to the undesired outcome, and both of them do not need to be present for the event to occur. NOT gates represent an inverse relationship between an input and an output. When the input condition occurs, the output event does not occur, and when the input condition does not occur, the output event occurs. In fault tree analysis, NOT gates are used to show how the absence of a condition can contribute to the top event. In simple terms, a NOT gate reverses whatever input goes into it. The use of AND, OR, and NOT gates in fault trees enables a structured representation of how individual events and conditions interact to contribute to a failure or hazard. By combining these gates in a hierarchical tree structure, fault tree analysis, FTA, provides a detailed and logical framework for understanding complex systems. This approach helps identify critical vulnerabilities, assess the likelihood of failure scenarios, and prioritize preventive or corrective measures to improve system safety and reliability. Logic gates are fundamental components of Boolean algebra, performing functions that sort or compile data. In fault tree analysis, investigators commonly use AND, OR, and NOT gates to represent causation. Additionally, exclusive gates, though less frequently used, can add detail to fault trees when needed. Boolean algebra relies on binary numbering, representing data using ones and zeros to model processes. This binary data is often organized in truth tables, which display logical relationships. For fault tree creation, truth tables typically represent outcomes as either positive or negative reactions. The table shown illustrates various logic gates, their graphical representations, and corresponding truth tables. Let's look at the basic fault tree from earlier in the episode and use the truth tables provided to see what causal factors are required for the top event to occur. Looking at our example fault tree, we can see a top event as well as 6 causal factors labeled A through F. Directly below the top event is an OR gate, and directly under that is another OR gate, as well as an AND gate and a NOT gate. Causes A and B are input into an OR gate. This means that if either A or B occur, then the output value of the OR gate is true. Cause C is input into a NOT gate. This means that if cause C occurs, then the value is false. But if cause C is not present, the value is true. Finally, we have causes D, E, and F, which all input into an AND gate. This means that all 3 causes have to be present in order for the output of the AND gate to be true. So what factors need to be occurring in order to trigger the top event? The inputs of the final OR gate before the top event come from the outputs of our other logic gates. Since it is an OR gate, this means that any positive output from below will cause the top event to occur. For our example, the top event will occur if causes A or B occur. The top event will also occur if event C is not present. The top event will also occur if all 3 other causes, labeled D, E, and F, occur at the same time. That can be written in Boolean algebra as A or B or not C or D, E, F. Let's use this fault tree in a case study about a fire at an office. Using case studies in accident theory is important because they provide real-world examples that help link theoretical models to practical situations. Case studies also highlight the complexity of safety systems, showing accidents rarely result from a single failure. In this case study, we are going to speak to Cheyenne, a worker in an office who had an incident. We will also look at the incident and develop a fault tree.
Hello, my name is Cheyenne. I have been working at the Abraxo Corporation as an office administrator for almost 1 year now. We have a laser printer in the copy room that we all use. This printer in the copy room had been there for years. One of those large, shared printers that everyone used for reports, training binders, and meeting handouts. You can tell this printer has been in the copy room for years, as it has definitely seen better days. It is noisy and slow, but it gets the job done. On the day of the incident, the office was busy but routine. People were printing documents throughout the morning, and the printer seemed to be running constantly. At first, nothing appeared out of the ordinary. There were no alarms, no warning lights, and no messages on the display panel. After some time, the printer started to sound different. The noise was louder and more strained than usual, but it still kept working. Since printers often make odd sounds, no one stopped it or reported the issue. A little later, a faint burning smell became noticeable. At first, it was subtle, and it was hard to tell where it was coming from. But the office started to fill with this awful smoke, the smell of burning plastic and chemicals. As the smell became stronger, someone finally opened the copy room door and saw smoke coming from inside the printer. Can you believe it? Our printer was on fire. At that point, it was clear that we had a serious problem on our hands. My coworker quickly unplugged the printer, grabbed a fire extinguisher, and safely put out the flames. Someone else pulled the fire alarm, and the building was evacuated. The entire building needed to be evacuated due to the smoke, and several workers needed to be treated for mild smoke inhalation by paramedics. It was freezing cold that day, and we were all stuck outside during this whole ordeal. None of us were prepared for the cold. I was worried that some of my colleagues would get hypothermia, or even worse, frostbite. After about an hour and a half, building management let us back inside. After a safety investigation, we found out that some of the internal mechanical components in the printer had been worn and were overheating. Protective devices that should have stopped the printer or cut power did not activate, and due to some construction in the building, the lack of a working smoke detection system delayed awareness of the problem. What seemed like a routine piece of office equipment, printing paper on a routine day, turned into an incident because multiple safeguards failed at the same time.
Let's create a fault tree based on Cheyenne's experience in the office. We will begin with the top event, which is the printer fire. We know that if there were an electrical short inside the printer, which we will label as cause A, or if the internal wiring became damaged and melted, which we will label as cause B, a fire could occur. This means that either A or B alone could result in the printer fire. However, should we stop our investigation there? Do we need to consider additional causes? Recall our discussion on bias and how jumping to conclusions can lead to a premature closure in an investigation. To avoid this, we need to dig deeper into what actually happened and reflect on Cheyenne's account. She mentioned that the printer was making unusual noises before the incident, which suggests that mechanical factors may also have played a role. Let's examine some mechanical reasons why a printer could catch fire. From an electronic standpoint, the printer could be functioning normally, but a counterfeit toner cartridge, which we will label as cause C, can also cause problems. The counterfeit toner could cause the fuser unit to overheat, which we will label as cause D, and if we combine that with inadequate ventilation, labeled as cause E, those combined causes could result in a fire. So does this mean that if A or B occur, or C, D, and E all combine together, there would be a fire? Modern electric devices, especially those that have the potential to overheat, all contain an import safety component called a thermal fuse. Let's add that fuse into our fault tree. To place the thermal fuse on our fault tree, which we will label as cause F, we are going to use a NOT gate. The reason for this is, if the thermal fuse is working, the NOT gate inverses the true output to a false. This means in order for the printer to catch on fire, there needs to be some sort of electrical fault, such as a short circuit or worn wires. Even if fake toner is being used, which causes an overheating fuser, if there is inadequate ventilation, the thermal fuse should detect this and shut the printer off before a fire starts. Therefore, the thermal fuse needs to have an output of false, which means its output is true because of the NOT gate, as causes C, D, and E in order for the printer to catch fire. A fault tree can range from very simple to extremely complex, depending on the number of causes, events, processes, and contributing factors involved. The analysis begins at the top event and works downward toward the underlying causal factors. As more information becomes available, the fault tree often grows in size and complexity. This means that fault tree analysis goes beyond a straightforward linear path from cause to effect. Instead, it reflects the reality that multiple pathways, conditions, and interactions can combine to produce a single adverse outcome. The complexity of a fault tree is also influenced by the investigator's ability to remain systematic, objective, and thorough throughout the investigation. Logic gates within fault trees, excluding NOT gates, can theoretically accept an unlimited number of inputs while producing a single output. This mirrors real-world systems, where numerous causal factors can converge toward one event. In practice, the number of potential causes is limited only by the quality of available data and the investigator's understanding of the system. For this reason, fault tree development is both a technical discipline and an analytical skill. Many safety professionals dedicate their careers to system safety, where fault trees serve as a critical tool for understanding complex systems, identifying vulnerabilities, and preventing future incidents. Think of a recent event that had some sort of negative outcome. Think of how many causes are realistically present and determine how those causes relate using fault tree analysis. Share your reflection in this episode's group chat or in the comments section if you are following on social media. In episode 14, we learned that fault tree analysis is a systematic hazard identification tool used to understand how multiple causes and conditions can combine to produce an undesired event known as the top event. By using logic gates derived from Boolean algebra, fault trees visually and logically map relationships between failures, safeguards, and outcomes, making them especially useful for analyzing complex systems. Widely applied in system safety, safety engineering, and risk management, fault tree analysis helps investigators identify vulnerabilities, avoid premature conclusions, and develop effective prevention strategies, as illustrated through the case study of a routine office printer fire caused by multiple simultaneous failures. Hazard identification tools are systematic methods used to identify risks that could lead to accidents or adverse outcomes. Fault tree analysis is a key hazard identification tool used to analyze the causes of an undesired event called the top event. Fault tree analysis begins with the top event and works downward to identify underlying causal factors. Fault trees use a visual, tree-like structure to show logical relationships between causes and outcomes. Fault trees are especially useful for analyzing complex systems with many interacting components. Logic gates derived from Boolean logic define how events and conditions combine to produce the top event. AND gates require all inputs to occur, or gates require only one input, and NOT gates represent the absence of a condition. Boolean logic uses binary values and truth tables to model system behavior and outcomes. Fault trees help identify critical vulnerabilities and assess the likelihood of failure scenarios. Practitioners in system safety, safety engineering, and risk management commonly use fault trees. Fault tree analysis supports effective communication, prevention strategies, and improvements in safety and reliability. Fault trees can range from very simple to highly complex, depending on the number of causes, interactions, and available information. COHSI provides its students with a multiple-choice quiz at the end of each episode, which can be used as practice material for the content that has been covered. A free version of the quiz can be accessed by anyone following our content on social media by using the QR code shown on the screen. If you are a COHSI student, please complete the discussion board topics found throughout this unit, as well as the episode quiz. Both of these tasks can be found under their appropriate tabs in your learning portal. If you have any questions or concerns, please reach out to your course instructor. Thank you for watching and have a safe day.